everyone. I am Faith Obiagumadu Woma,
And I am Hilary Chukwuma.
and we are representing Group 2. And this is our project on credit card fraud detection using machine learning and explainable AI. It was developed in R for CSC 312. Now, in the next few minutes, I'll briefly explain the problem we are solving, the data sets we used, how we built our models, and the results that we got. So, what exactly is credit card fraud? It's when someone uses another person's card or card details without permission. And as online payments become more common, this has become a much bigger issue. And this costs banks billions every year. And the difficult part is finding fraudulent activities is actually very rare. And in our data sets, it takes about or less than 0.2% of all the transactions. So basically, finding it is very difficult. Now, at the same time, banks cannot afford to wrongly block genuine customers so that the system has to be accurate and reliable at the same time. Now, that is where machine learning comes in. Instead of relying on fixed rules, it learns from the patterns of previous transactions that have been done over time, and explainable AI helps us understand why the model makes a particular decision instead of simply accepting its prediction. Now, the challenge we wanted to solve was very simple. We asked a simple question. How do we correctly identify the very small number of fraudulent transactions among hundreds and thousands of legitimate ones? Now, following the traditional rule-based system does not adapt well because fraud methods they keep changing and they also generate too many false alarms. So our goal was to build a smarter model that could detect fraud accurately while still being very easy to explain. And to achieve that, we set a few objectives. Firstly, we prepared and cleaned the data. Then we handled the class imbalance. And after that, we explored the data, we trained it, we compared three different machine learning models, we explained how the best model makes its decisions, and it finally built a simple prediction system. For this particular project, we used the popular ULB credit card fraud dataset from Cargo. It contains about 285,000 real credit card transactions collected over 2 days in 2013. And out of all those transactions, only 492 are fraudulent. Now, the dataset has about 31 columns with no missing values. Most of the variables ranging from V1 to V28 were anonymized so that customer privacy could be protected. And while time and amount remained in the original form, we scaled those before training our models. Over to you, Hilary.
Alright, our workflow followed a typical machine learning pipeline in R. We loaded the data, cleaned and scaled it, explored it visually, balanced the classes, split the data into training and testing sets, trained the model, evaluated them, and finally interpreted the results. One important thing we did was to make sure that the data sets still reflected the real world fraud rates so our evaluation will be realistic. Since this is an Arrow project, here's a quick overview of the tools we used. We stored our data in data frames. We used deploy Arrow and pipes to process it, and wrote our own functions to keep the code organized. For visualization, we used ggplot2. Then we built our model using GLM, Arrow paths, and random forest. To balance the datasets, we used the rules package, and PROC helped us evaluate the model performance. Now, during our analysis, two things became very obvious. The first was the severe class imbalance. The fraud cases were very tiny compared to the legitimate ones, which you can clearly see in the bar chart. The second was some variables consistently showing stronger relationship with fraud than others. Features like V17, V14, V12, and V10 stood out. As you'll see later, they remain important in our final model. Alright, over to you.
So literally, we trained three machine learning models. The first one was logistic regression, which is easy, it is fast, and very easy to interpret. The second one was a decision tree. This one makes decisions using rules but can easily overfit the data. Finally, we trained a random forest, which combines the predictions of 100 decision trees, making it much more accurate and reliable. We believe that a model shouldn't just predict fraud, but it should also be able to explain why. For explainability, we relied on feature importance from our random forest model together with our earlier correlation analysis. Now, instead of using external tools like Sharp or Line, we chose a simpler approach that still clearly showed which variables had like the greatest influence on the model's decision. Coming down to our results, logistic regression and the decision tree each detected about 90% of the fraudulent transactions. However, they also generated a very large number of false alarms. Um, the random forest, on the other hand, detected slightly fewer fraud cases, about 87%, but its precision increased to around 60%. But its balance detection and false alarms much better. It achieved the highest F1 score of 0.71, making it our best performing model. Another very interesting result was the feature importance. The random forest identified V14, V17, V12, and V10 as the most important variables. These are almost the same variables that appeared during our correlation analysis. Now, seeing two different methods produce similar results gives us a greater confidence in our model. All right, over to you, Hilary.
Okay, now based on everything we've observed, we selected the random forest as our final model. Although logistic regression recorded a slightly higher AUC, it also produced far too many false alarms. The random forest offered the best balance between detecting fraud and minimizing unnecessary alerts, making it more practical for real-world use. One of our major challenges was the class imbalance, which was addressed through oversampling. Another challenge we've encountered was finding the right balance between detecting fraud and avoiding false alarms. Also, because many variables were anonymized, we could identify which feature were important, but we couldn't explain the real-world meaning. I want to. In summary, we developed a complete fraud detection pipeline in RO, starting from raw data all the way to a working prediction model. Among the three models we tested, the random forest performed best with an F1 score of 0.71, while remaining interpretable through feature importance. Overall, our project shows that a good fraud detection system should not only be accurate but also explainable. For future improvements, we recommend training the model with newer data sets, experimenting with deep learning methods, deploying it for real-time fraud detection, and using tools like SHAP to provide transaction-specific explanations.
And this brings us to the end of our presentation. Thank you very much for listening, and we will be very happy to answer any questions.